So, welcome to a new series in computer organization. So, what this video series is going to be is really more of just me sort of video journaling my process as I learn computer organization. So, I don't really know who needs to see these videos, but I figure I'll just make them anyway in case anybody I don't know is studying computer organization, looking at similar material, and just wants to see a thought process as I learn the content. So, in any case, the way that I'm approaching this is I'm going to this fairly famous website, Teach Yourself Computer Science, and going to computer architecture, and in particular using this CS61C course, which is a leftover website for a Berkeley class. And I'm going to just do the homeworks and think out uh, how I approach the solutions to these homeworks, and hope that's of some value to somebody. Um, might as well just jump right into the first problem. So, uh, so in this first problem, we're going to be looking at number representation, and so we're going to assume that we're working with 8-bit numbers, and um, and we're going to be converting these binary 8-bit numbers. So you can see that there are 4 bits here and another 4 bits over here. So those are the 8 bits. This leading 0b just indicates that they're binary numbers. And in this first part of the table, we assume that everything here is unsigned. What that means is that we're dealing with non-negative numbers, right? So you just can't have negatives. And therefore, we can already say in this row that the two cells that go for the other numbers is just going to be NA, NA, right? Does not apply because you cannot represent in an unsigned way some negative numbers. So in any case, so yeah, and let's just for the sake of confirming that we're doing things right and so on, let's just check that this like how would you get from the binary number here to the decimal number that is here? And so let's see the process. Well, initially these leading zeros are not necessary, right? The only part that we need, this is kind of familiar to all numbers, is that those leading zeros are unimportant. And so maybe I'll represent the number like this, right? So that 0b, again, just indicating that this is to be read as a binary number. And we're going to start processing this number into a decimal, which is to say base 10. So how do you do it? Well, there are a couple different algorithms, but I think the one that I'm going to use here is to take that rightmost bit, which is a 0, and I have a rule for that rightmost bit, which is what you can kind of think about just for the logic of it is that if the rightmost bit is a 0, then it must be an even number, and is divisible by 2. And so you can factor out a 2. So I could say that this is 2 times. And then everything that's left over after you divide by 2, and if you take any binary number and divide by 2, it's effectively the same thing as bit shifting it. So I'll represent that what's left over is the bit shifted binary number 101. And so this is going to be my first step in the algorithm for computing this change of representation. And so yeah, and so like but you can see that this leaves you with another binary number, smaller, so we're making progress, but you have to do it again. So let's say that 0b 101 turns into, well, now I have the rightmost bit is a 1, so I'm going to have a rule which is very similar, which is effectively that I just split the 1 off, right? So there's going to be like a +1. But what I'm splitting it off, right? If I remove that +1, then I have a 100, right? So if you imagine that this 1 is getting split off, then once it's split off, what remains is a 100. And so I apply my rule for having a 0 in that place. So that's 2 times 10, right, as a binary number. So effectively I took the right, when there's a 1 here, I split it off. And then once it's split off, I use my rule for what you do when there's a 0 bit in the rightmost bit, which again is to write it down as a times 2. And then what's underneath the times 2 is the bit shifted binary number. Okay. So that's the next step of the algorithm. Now we're looking at the binary number 10. And we do it again. So that means that I just do 2 times the bit shifted number, right? Because again, right, the rightmost digit is again a 0 in this line. And then once you get down to a single digit number, of course, right, that doesn't present any particular issue. I might as well just say, well, that just turns into 2 times 1, which is 2. So having done that, right, so we now know that up to here, right, this whole thing is just the number 2. And so if that's just the number 2, then I can come back up here and say, well, this then turns into 2 times 2 plus 1. And that's the same thing as 5, right? Just doing regular arithmetic on those numbers. So that's the number 5. And then, well, since I've basically determined that this is the number 5, then I can come back up here and say that that then turns into 2 times 5. And then the whole thing is the number 10. And that's how we get this decimal number. Okay, great. If we want to convert the binary number into hexadecimal, right? So I guess I should maybe like indicate that this is where I did my row 1. And in particular, this is binary to decimal. And so down here, I'm going to do